are going to talk about the IoT standards and communication protocols. Again, I'm still code Janvier. So now here we can see at the right side we have a picture that shows different hardware systems, and you can see different links that interconnect these hardwares, guys. Then we say the Internet of Things. Its purpose is to bring together the heterogeneity of physical devices to communicate and share information. So, guys, as a human, you can share the information with your friend, maybe through communication. This communication can be facilitated by a common understanding language. Let me say, if you are in a Commonwealth countries, you can communicate by using English. If you are coming from Francophonie, you can communicate by using French, or even you can communicate by using the sign language. So how do you think now the hardware devices that manufactured from different companies, different manufacturer industries can communicate or share information? So traditionally, the hardware would be useless because this communication cannot be happen. So to allow the hardware to communicate and share the information collected via sensors, there we need a transport medium. We need a common understanding language. So this hardware language here is being implemented, so-called protocols. So the protocols, it enable those smart devices to talk and interact. So the device interaction is only possible when there is a common medium of communication, like a common language that all devices in the given IoT ecosystem would share and be able to use it. So within the IoT ecosystem, this communication medium is being facilitated by IoT communication protocols. So these protocols can be implemented by using existing internet protocols or the IoT protocols that comes out by the merging of IoT technologies. So without the IoT protocols, the hardware would not be able to communicate the data they have captured. So this is why we need the standard of IoT protocols that the IoT ecosystem would use for allowing those different devices to communicate and share information. So now what is the Internet Protocol Suite? The Internet Protocol Suite defines a collection of protocols that are designed to work together to deliver services in the public internet communication. So the Internet Protocol Suite It defines a set of communication protocols used in internet communication. Mostly it is known as so-called TCP/IP because these are the main protocols that are being used in this scheme. So now, how could we now define what is a protocol? So a protocol can be defined as the rules that governs how the systems communicate. For networking, they govern how the data is transferred from one system into another. So the protocols can define how this IoT system can communicate and how even the data can be transferred from one system to another. So here we have a comparison between the IoT protocol suite and the Internet protocol suite on the left side. So the first layer is the link layer, which defines the infrastructure level or physical layer of the Internet protocol suite. Here it defines the physical medium, defines different protocols that are being used in this infrastructure layer. These include Ethernet protocols or standard and even wireless local area network standard. So the second layer it is a network layer. Here this a network layer it defines how the information packets could be transmitted from the host device to the destination one. Then it defines different IP, different protocols like IP version 4, IP version 6. Then we have the transport layer. Here the transport layer, it uses TCP and UDP protocols. The TCP it means it is now the transport control protocol. Then UDP is called the user datagram protocols. Here this layer is to control the connection between the host and the destination. Then lastly we have the application layer, which defines different protocols that are used for delivering services to end users. These protocols include HTTP, like a high hypertext transfer protocol, FTP, file transfer protocol, and the simple message transfer protocol, and even the others. So at the left side now, we do have the other layers where the bottom one is the link layer. Again, this link layer, it defines the infrastructure level of the communication. It includes different communication networks or protocols like the Wi-Fi, like GSM, Bluetooth, LoRaWAN. So these are some of the protocols that are used in this link layer on the side of the Internet of Things. Then the next one, we do have network layer. So here the network layer, it defines the IP version 6 and the IP version 6 over low power personal area network. So now what is the difference between these two entities? Okay, so normally the public internet communication uses so-called the IP version 6 and the IP version 4 for trying to identify or to provide the unique identity to every devices connected on the network. But there is by merging of the IoT devices, we have an issue of the devices which have to run on battery powered. And we expect those devices to operate for 20 years and even above without recharging those batteries. So if we try to relying on those existing IP version 6 or 4 for the IoT communication, we would face an issue of power because the IP version 6 it consume a huge amount of power consumption, which cannot be supported by the constrained IoT devices. So, for implementing the IP version 6 in IoT constrained devices, now the 6 low pan was implemented. So you can say the 6 low pan is the implementation of IP version 6 in IoT communication. Then, on the transport layer, we have so-called UDP, User Datagram Protocol, and you have TCP for ensuring the reliable communication between the host and the destination. Then lastly, we do have application layer which defines different protocols that would be used for serving the end users. These communication protocols include HTTP, MQTT, message queuing telemetry transport protocol. We have COP constrained application protocol. We have even advanced message queuing protocol and the hypertext transfer protocol. So now let's talk about in details for each layer mentioned in the IoT protocol suite. So first one, we have the link layer. I told you this link layer, it is the infrastructure level, and it defines a variety of different technologies used for allowing the end devices to communicate and exchange data. So these protocols or technologies include so-called WiFi, Bluetooth, WiMAX, Zigbee, Cellular, LoRaWAN, RFID, Wi-Fi High-Low, Sigfox, Narrowband IoT, and Waitress. We can even have more on this. So we're gonna now later describe each and every one. So now what is now IEEE 802.15.4. So this is the common IoT standard defined for medium access control, and it defines how the message or the frame will be formed. It defines the length of the headers, include the source and even destination address, and how the node can communicate and each other. So it contains this information. So this standard actually 802.15.4. It is mostly designed for the internet communication. So when we go for the IoT communication, it is still heavy and it consumes a huge amount of the power consumption. Therefore, accommodating the IoT communication system, it has enhanced into 802.15.4. We add E, which means extended. So we allow this IoT standard to accommodate low power communication and meet the IoT communication requirements. So we do have now IEEE 820.11a8. So without now adding AH, IEEE 820.11 is the wireless standard communication protocol, which is known as by Wi-Fi. So anywhere you can lead from any device, like IEEE 802.11, it defines the Wi-Fi communication. You have to know this device is used for Wi-Fi communication. So again, this original Wi-Fi communication, again, it consumes a huge amount of power. Then for allowing the IoT ecosystem to communicate by using the Wi-Fi communication, we add on top of this Wi-Fi standard, we add on AH, which means Wi-Fi Halo. So this Wi-Fi Halo, it allows the IoT application to communicate by using Wi-Fi standard over low power consumption. We can see that this standard operates in the sub-gigahertz band around 900 megahertz. Then we have the Bluetooth low energy. So the Bluetooth low energy, as you know, we all have the Bluetooth in our smartphone, in our computers, which can allow the devices to communicate at a low distance or short distance without an internet connectivity or Wi-Fi connectivity. And sometimes this Bluetooth communication can reach maybe within 10 or 15 meters, but it depends on the technology. We can have even enhanced Bluetooth communication, which can reach 100 meters. So it depends on the technology that the Bluetooth is using. So now, what is now the Bluetooth low energy? So the Bluetooth low energy, it is the short-range communication protocol. It is being used for short communication. It is the version of the classical Bluetooth enhanced for allowing the communication very faster and even at low power consumption. So we do have now so-called Zigbee. It is based on the IEEE 820.15 communication protocol standard, as you have seen before, and it is used for personal area network. So now the Zigbee, it can allow the IoT devices to communicate or to share information wirelessly within 100 meters. The Zigbee standard operates on IEEE standard 802.15.4 physical radio specification, and it operates in unlicensed bands including 2.4 gigahertz. It means you can use it freely without any cost because it is using unlicensed bandwidth. And you can see the frequency of operation is 2.4, the same for the Wi-Fi communication. The range of Zigbee communication is very small and is allowed between 10 and 100 meters. So there are three types of Zigbee devices in a Zigbee network. One is called the full function device. The other one is called the reduced function device. And lastly, we have so-called the Zigbee coordinator. So now let's describe each and every device. These are full function device node can be additionally act as the router. Then the Zigbee system, as mentioned, contains three different types of device: Zigbee, coordinator, router, and end device. So every Zigbee network must have at least one coordinator which acts as the root or bridge of the network. The Zigbee coordinator, which is responsible for handling or storing the information while performing, receiving, and transmitting the data between different nodes of the network. Then we do have Zigbee routers, which act as the intermediary device that permit data to pass to and through to the other devices. Lastly, we have the end devices, which have the limited functionality to communicate with the parent nodes, such as the battery power is saved. So these end devices are not able to communicate with the parent node because of the issue of the power. Then they need the routers, which act as the intermediate devices to allow the data to be transmitted from the one any device to another, or from any device to parents. So here we can see we do have the image of the Zigbee device, and the Zigbee device can be used in different topologies. We do have style topology. As you mentioned, every network can have at least one Zigbee coordinator, and within these different topologies, the red one is the coordinator or the bridge. Then the yellow one is and the any devices. Then the blue one is the Zigbee router. So every Zigbee network can have at least one coordinator and the many other devices. So the Zigbee router is not a mandatory to be available in every network, because the router will be used for helping the devices with limited capability to communicate, to allow them to exchange the dollars and so on. So we have now so-called the long-term evolution. This long-term evolution advanced is a set of standards designed for machine-to-machine communication and IoT application in cell network. So it is designed to allow the IoT to be facilitated by cellular network. So this long-term evolution advanced is low power protocol compared to other cellular network. So we do have now so-called the RFID. The RFID means radio frequency identifier. So this radio frequency identifier, or known as RFID, it contains a couple of tags. We have RFID tag. You can see on the left side, and it can be a normal card like the tap and go. So it can be implemented like the key holder and so on. Then we do have the bottom one, what you can say RFID reader. So the system, how it operates. The RFID tag actually contains a unique numbers. So these are unique numbers. It differentiates from one RFID tag from another one, which means every RFID tag contains its own unique identification. It is not possible to have two RFID tags containing the same number. So this information is saved on the chip that is implemented inside this RFID tag. Even you can't see it by your eyes, but inside we have a chip that contains electronic information. So mostly this This is set to communicate. The RFID tag is being attached to the device that you want to track. Let me say you want to monitor the library, how the students are using the books. You want to check if there is no thief or if the student cannot steal the book from the library. So what you can do, you can paste or you can attach for every book in the cover of the book, you can integrate an RFID tag, which means this RFID tag contains the information about the book, including even the identity or electronic number of the book implemented by the chip. So then, at the exit or the entrance of the library, what you can do, you can design and implement a monitoring system that contains an RFID reader and a microcontroller, which is going to detect or to scan any nearby book. So if the book is nearby the system, it doesn't need to be attached. Here it can even be a wireless system. So the lead this RFID reader is going to capture the information about the card, and in collaboration with the microcontroller, the system is going to monitor if the books has been allowed to go out of the library or not. If the books is not allowed to go out, the system can automatically call the library manager. It can even automate a ring or even another warning system for saying there is an allowed access to the certain books and so on. So the RFID reader first can be used for security system, mostly for tracking the object. So the radio frequency identifier is the wireless use of electromagnetic field to identify the object. So this RFID reader, it uses an electromagnetic waves for identifying nearby RFID tag. The RFID tag is also attached to any object such that its production and the manufacturing process can be tracked through an assembly line. So at the assembly line, you can attach the RFID tag for every item that is being manufactured so that it can be tracked. Usually, you would install an active reader or reading tags that contains stored information, mostly authentication replies. So the RFID reader should be able to read the information from the RFID tag by using electromagnetic waves. This RFID reader communication is a short-range communication and is about 10 centimeters, but it can reach even to 200 meters based on the technology you are using. Now we do have so-called LoRaWAN. So the LoRaWAN, which means long range communication, wide area network. This is the technology or IoT communication technology that is being used for allowing the end devices to communicate with the gateway wirelessly without the internet communication. The devices that are using the LoRa communication, each end devices must have the LoRa communication capability, and the gateway can have the LoRa communication capabilities. Then between the gateway and the end device, the device can be exchanging the data without the internet communication. So this LoRa communication is wireless technology designed for low power wide area network, which means it can go to far away of kilometers without an internet. So it can be bi-directional communication. Data can be transmitted from the end devices to gateway, or even from the gateway to end devices. So it allows the low power consumption, and it is done for scalable wireless network within millions of devices. So the range of LoRa communication, it is not specifically defined. So some researchers says the LoRa communication can go around 15 kilometers in urban areas, or it can be even 15 kilometers in the rural areas, and around 5 kilometers in the urban areas. But this information are not only, I can say, are not the last ones, the information. The research is still in progress. I have read somewhere that the LoRa has been tested on the sea with line of sight between the end devices and LoRa communication, and the LoRa communication was able to allow two end devices to communicate over 500 kilometers without an internet communication. So if you want to add the communication range of the LoRa communication, you can allow two end devices to communicate by using line of sight. Now we have so-called narrow band IoT. So this narrow band IoT, it will allow the cellular communication network to add on new nodes that will allow the IoT devices to be served with low power consumption, which will allow the mobility in the IoT ecosystem. You all know the cellular network covers almost every area of the country. So if we accommodate, or we give the BTS the capability to serve the IoT devices, we are going to accommodate billions of the IoT devices only to communicate via nearby the base station at low power consumption. And the other advantage we have you know, the cellular communication is a wide communication area network. So we are going to profit this benefit of cellular network, and even at low power communication. Narrowband IoT is also known as Long-Term Evolution CAT NB1. It is low power wide area technology. It connects devices more simply and efficiently on already established mobile networks and handles small amount of data securely and reliably. This protocol can be deployed into existing network infrastructure. It is promised that every technologies will be included in the IoT cellular communication network. So the narrowband IoT, it is a new technology that gonna be included in the 5G cell network that will allow the existing mobile network to serve the IoT devices, to allow the devices to communicate and share information through the existing cellular infrastructure. So if you don't have any question, we are going to take a break
No question.
of 15 minutes and then we come back.